Welcome to the Bodhi Academy. My name is Amisha Kulaso, and in today's video we will continue with our class 12 chapter 2 electrochemistry. So in the previous video of this chapter we learned the meaning of the term itself, that is the electrochemistry term, and we defined the two major processes that occur. One is we go from electrical energy to chemical energy, and the other we go from chemical energy to electrical energy. So previously we discussed about the Daniell cell, that is an example of the electrochemical cells in which chemical energy is getting converted to electrical energy. Now we will see how further this process gets modified into the electrolytic cells. Okay, so previously we talked about how zinc being the rich one, it will donate its electrons, correct, and these electrons will flow here. So the electron flow will occur in this direction and the current flow occurs in the opposite direction. So the electron flow occurs and the electrons get over here, and from here this Cu2 plus which is present, they begin to pick up this and they form as Cu with zero oxidation state on this cathode. Okay, now in today's video we will look at the possible situations what will happen if we decide to apply an external potential. Okay, so currently here consider that the potential of the cell is E. Okay, now consider that the potential of the cell is E. Now what I am saying is that I am applying a external potential. I am applying a external potential to the cell and I call it as E external. Okay, E subscript ext. So I am applying a external potential to the cell. Now when we had the potential E, what was happening? The electron flow or the potential difference, electron flow was happening from where? From anode to cathode, correct? So it was going from anode to cathode. Now if I apply an external potential, what the external potential will want to happen is that it will want to reverse the system. Reverse as in the electron flow will occur from the cathode to the anode. So this was when we have E potential and E external potential. If we apply, in that case the electron flow will want to reverse itself. Okay, so it will want to go from cathode to anode. Now in such thing we have three possible situations that will happen. Okay, so three possible situations. Now the first one, say now E external is less than E. Now in this case, say I am applying a E external force which is comparatively less than the already existing E potential that is present, correct? So now in this case what will happen? Even if I apply my potential, that is E external, the E which is already present over there is much higher, correct? So therefore it won't allow the system to reverse the flow of electrons. The flow of electrons will continue from anode to cathode itself. So in this case E external is less than E. Okay, so the potential that I am applying from outside is less than E. In this case the power won't be so much. The power, it won't be so much, correct? Now therefore what will happen? The electron flow will continue its original path. It will continue in its original path, that is from anode to cathode. because the potential that I am applying is not able to overcome the already existing potential. Okay, so if you want to overcome a force, that means what, you have to apply a force that is greater than that, correct? So in this case, if I am applying such a less external potential, then it won't be able to overcome the already existing potential. So in that case, what will happen, the electron flow will continue in its original path, that is from anode to cathode. Next, say my E external, I am applying it equal to E or E which is already present. In this case, what will happen, they will have the same amount of potential. So if I am applying my potential from this side and the already existing potential is coming from this side, now their power is so much equal that none of them will let the other electron move towards the other side, correct? So in this case, what will happen, there will be no flow of electrons at all, and therefore no reaction will occur. And the last case is E external is greater than E. Now in this case, what will happen, E external being the powerful one, it will overcome the existing potential. It will overcome the existing potential E. Okay, and therefore what will happen now, the flow of electrons will reverse from cathode to anode. Okay, now when this reverse is happening, now the electrons are flowing from where, copper to zinc, correct? Now in that case, what we are doing, we have reversed the whole system. So now what will happen, previously what was happening, zinc was giving away its electrons and it was going into the solution as Zn2+. Now what will happen, copper will give away its electrons and it will go back in the solution as Cu2+, correct? Now this is not typically supposed to happen because zinc being the richer one won't ever ask for electrons. But what are we doing different here is that we are applying a external potential which is forcing the system to go in the reverse direction. Now when this reverse direction occurs, the whole system undergoes a change and this change leads to the electrolytic cells. Electrolytic cells is the conversion of electrical energy to chemical energy. So what are we doing here? We are applying a external potential, that is the electrical energy, which is forcing the chemical reaction to occur in the reverse direction. Understood? So this is the basis of how electrochemical cells shift to electrolytic cells. About electrolytic cells we will discuss ahead, but now we will discuss some of the important terms in this chapter. Now the first term is the standard electrode potential. Okay, now to understand standard electrode potential, let's go back and understand what is electrode potential. Okay, so now in this system, what do we have? Two things, major things that we have is we have these electrodes and we have this solution. The solution is also known as the electrolyte. Okay, so now electrode potential, when we say, it is the potential difference that is created between this electrode and this electrolytic solution. Understood? So see here, it is given electrode potential is the potential developed between the electrode and the electrolyte. Now when I say standard electrode potential, it means that this same electrode potential, but we are considering it under standard conditions. Now when I say standard conditions, the temperature will be 298 Kelvin, pressure has to be 1 atmosphere and the concentration has to be unity, or we can say 1 molar or 1 mole per liter. Okay, understood? So standard electrode potential is basically same as electrode potential, that is the potential that is developed between the electrode and the electrolyte. Only the difference that is present is that it undercomes over the standard conditions, that is the temperature should be 298 Kelvin, the pressure should be 1 atmosphere and the concentration should be unity, that is 1 molar. Now the standard electrode potential, it is denoted by E and this knot on top, that is the superscript knot that we add. Now this can be again subdivided into what are the two processes happening, one is reduction and one is oxidation. So we will have standard oxidation potential and we will also have standard reduction potential. Now if I have to write this standard oxidation potential, how will I write it? So in general we start with writing E naught, correct? 10. Say you have a metal M. Now in oxidation what is happening? The metal is going from 0 state to +2 or any N state. Okay, it is getting oxidized. So we write it as M/Mn plus. Means any metal from 0 state, it is getting oxidized to some other oxidation state. In standard reduction potential, it is exactly the reverse of it. So we write E naught and it will be Mn plus, that is the oxidized species is getting reduced to 0 oxidation state. Okay. So now same thing, if I have to write for the above equation, that is this one, how will I write it? See, we have E naught will be equal to what? Here, so, subscript we have to write it as. So Zn is undergoing oxidation and it is going from Zns to it is going to Zn2 plus, that is the aqueous form. And secondly we have E naught, that is going from Zn, we have copper, so it is going from copper 2 plus, that is aqueous, to Cu, that is 0 oxidation state. Here also 0 oxidation. Understood? So this is how you can denote the standard electrode potential of any given cell. Now let's understand the next term that we have, that is cell potential. Now when we were talking about electrode potential, we said that it is the potential difference between the electrode and the electrolyte, correct? Now when we say cell potential, means we are talking about the two cells that are present. Two cells, as in the cell has how many electrodes? We have two major electrodes. So now when we say the cell potential, we refer to the potential difference between the two electrodes in any given cell, may it be galvanic cell, voltaic cell, Daniell cell, any cell. In that, it is a potential difference that is created between the two electrodes of the cell, and that is denoted by E subscript cell. Now when we looked at standard electrode potential, what we said, we were looking at the oxidation potential and we were looking at the reduction potential. Now the next question we will ask is, which potential are we, or which cell potential are we talking in this case, oxidation or reduction? Now, so which difference are we talking about, the oxidation potential difference or the reduction potential difference? In standard electrode potential, we were having both of them separately. But when we talk about cell potential, by convention, that is, I mean by rule, we only look at the reduction potential. So we only look at E reduction. So E cell will be only equal to the reduction potential. So we never look at the oxidation potential when it comes to the cell potential or the E cell. Now next topic is, how do we represent any given galvanic cell? Okay, so now we have that whole diagram, correct? So in that case, every time we cannot draw the diagram to show the depiction of the cell. We need some representation or some short form to tell that this and this is a cell reaction. So now a galvanic cell, it is generally represented by putting a vertical line between the metal and the electrolyte solution and putting a double vertical line between the two electrolytes connected by a salt ring. Now say example is this, Zns, Zn2 plus aqueous and Cu2 plus Cu. So what does it say? First we have to start by writing the metal. So metal is what? Metal is Z. Metal is Zn, correct? So that is the metal. So S. Next, then what you have to do? You have to put a vertical line between metal and the electrolyte solution. So this is the vertical line that you have to put. Now next is the electrolyte solution. So electrolyte solution here is ZnSO4, correct? That is aqueous. Now then what you do? You put a double vertical line. This double vertical line, it represents the salt bridge that is present. Then you do the same for the next metal. So you have the second metal, that is Cu2 plus and then you have CuSO4. Okay, so this is the two things which are present. Okay, one, this is in zero oxidation state, so Cu2 plus. So this is how you can represent any given cell which is given to us. Now next let's talk about something known as the standard hydrogen potential. Now what does the standard hydrogen potential mean? Okay, one correction here. So this is given as, you write it as CuSO4. We are going from CuSO4 to Cu, or you can write this as ZnS to Zn2 plus, then 2, then Cu2 plus to Cu, that is S, and these are in the aqueous form. Okay, so you have to write the metal, the solution, the metal and the solution in the same way between the two electrolytes. So sorry, here you have to write the two electrolytes that are present, because the salt bridge goes into the electrolyte solution and not the electrode. So you have to write metal, electrolyte, electrolyte and metal. Now let's talk about the standard hydrogen potential. So standard hydrogen potential, it is basically represented as SHE. Now the significance of this is that it is zero, its value is zero at all potential. So that is the reason why this SHE is used as a reference electrode, because it won't show any potential in that case. It is used to determine the potential of the half cells and can also act as a cathode half cell as well as a anode half cell. So see here we have the cathode half cell reaction. Cathode half cell, we know it undergoes reduction. So H plus, that is a proton, it will gain one electron and it will become H2, correct? So H2 is a pure gas, so it will go out as a gas. Then at the anode what will happen? Oxidation. So what it will do? It will give away its one electron which it has and it will become a proton. Now in both the cases, when you try to measure the potential which is present, it is coming to be zero in oxidation as well as reduction. Now the standard hydrogen electrode, it consists of a platinum electrode coated with platinum black. The electrode is then dipped in the acidic solution and pure hydrogen gas is bubbled through it. This concentration of both the reduced and the oxidized forms of hydrogen is maintained at unity, that is the concentration is around 1 molar. This implies that the pressure of the hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. So this is all happening at a standard condition. So see here, this is the, so it consists of a platinum electrode. Here this is the platinum electrode which is coated with platinum black, and then it is put up into this acidic solution which is of mostly H2SO4, and this happens all at standard conditions. Okay, so now we'll look at how to measure the electrode potential of a given cell. So the electrode is connected to a standard hydrogen electrode to constitute a cell. So this is C. Look at this system. So this is our anode, that is we have the SHE. This is the standard hydrogen electrode here, and this is the cathode that is present. So the electrode forming the negative terminal of the cell is allotted negative value of electrode potential, whereas the electrode forming the positive terminal of the cell is allotted a positive value of the electrode potential. So this is the positive and this is the negative terminal. The potential difference developed between the two terminals is measured using the potentiometer. The direction of the flow of electric current in the external circuit is used or is identified using a galvanometer. Now this enables us to identify the positive and the negative terminal of the setup. How? Defining where the current is flowing. So the current flows from the positive terminal to the negative terminal. This in turn will help us mark the anode and the cathode electrodes due to the fact that the electrons will flow from the anode to cathode. So if the current is flowing from cathode to anode, it means that the electron flow is reversed. So it will go from anode to cathode. So each cell is calculated as E cathode minus E anode. Now in case of Daniell cell, so we know here, see, in case of Daniell cell, in the anode section we have the Zn, so anode will undergo oxidation, and at cathode will have reduction that is occurring. Okay, so now look here, in case of Daniell cell, at anode there is oxidation, that is what, loss of electrons that is happening. So Zn, it will lose its 2 electrons and it will go into the aqueous form. At cathode again now reverse is happening, that is reduction by gain of electrons. Copper which is there in the solution form, it is waiting for electrons to come and grab onto them. So Cu2 plus the electrons, it will go in Cu. Now the net reaction of this cell is the sum of the 2 half cell reactions. Half cell is in the oxidation half cell, that is Zn, and the reduction half cell, that is copper. So EMF of the cell is given as E cell equals to E cathode minus E anode. So E cathode, the value is 0.34, and for E anode it is minus 0.76. Now these values are specific here. Measured EMF of Cu is 0.34, that is of copper, and of zinc it is 0.76 volt. So this is minus 0.76 volt. This is minus 0.76 volt. So therefore 0.34, this minus, and this minus 0.76 volt. So you have to add them together and you get the EMF of the cell, that is 1.10 volt. So similar way, if any cell is given to us, knowing the EMF values of the individual metals, we can find the E cell or EMF of the cell that is given. Okay, so that was it for today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.